Okay, so hello everyone. Hopefully you can hear me. So let's first recap what we have done yesterday. And this was our first program, which uh, we used to summarize the data in one arbitrary array using a parallel programming. So first, in lines from 19 till 30, we used a cyclic decomposition, and I will explain this once more. So in cyclic decomposition, when we have a vector or an array of elements like this, and so on, and when we have processes, let's say process 0, process 1, process 2, 3, and so on. What we are doing is that each of the processes is starting at its own index. So at index 0, 1, 2, 3, and so on. And then the next index that it should process is by, let's say, NP amount larger, where this NP is being the number of processes. So if number of processes is 10, here we will have P9. Then the 0th process would process 0th element, then 10th, then 20th, and so on. And so on. So for each element, the processes will jump by an amount of by a number of processes until the end of an array. So in a cyclic manner, each process is starting with its own ID or rank. Then it is going all the way up to the end of the array. Let's say it has a length of n, and it is skipping the number of processes. Let's say NP, or in our code it was size. So this was done here. So this I means the index or the rank of a process, n is the size of an array, and size is the number of processes. And then based on these indices, we created a smaller chunks of data. This was main data, main vector, and then we copied the values into the smaller chunk and send them to appropriate process. If we are the 0th process, then we already have this data, so we just say my data is equal to chunk. Otherwise, we are sending the data to the process with an rank or index I. So this was done only at the 0th process. If we are not a 0th process, what we are doing, we're expecting from it. From 0th process, we're expecting to receive the data. And both of these calls, both send and receive, are blocking calls. So what that means? That means that we have, let's say, process 1, process 2, and this process, or process 0 and process 1, to say like that. And when this process comes to the line send, it is waiting. It is waiting until somebody is trying to receive that. Also, here receive. Let me just type because it's smarter. Also, this call is a blocking call. So once the process 1 reaches the line where it has the receive function, it will wait for somebody to send the data. It will not continue until it receives. This, of course, can cause sometimes issues. If you write bad code, your code can lead to something called a deadlock. That happens when two processes are waiting for each other to complete a communication function. So maybe both are trying to receive something that the other one has, and they are blocked there. So maybe something like this. Receive A from process 1, and he says receive B from process 0. Then he says send B to process 1, and then he says send A to process 0. So this would lead to deadlock. The process 0 reaches this line, then it waits for the process 1 to send him the value A. The process 1 goes to receive function receive B from the process 0. It is asking for process 0 to receive B, but process 0 is waiting on A, and they're waiting for each other there. The solution to this is very simple. Just change the order of these in one of the processes. If we put function calls like this, send, then receive, and here receive and then send, then everything is okay. The process 0 is asking to receive a value. The process 1 is sending a value, so this completes. Then the process 0 is sending a value B, and the process 1 is receiving a value B. So this is okay. This is not. It will lead to deadlock. So be careful when you write these kind of functions. Okay, here everything is okay because only the 0th process is sending the data and everybody else is receiving the data. What we can also note here is that communication runs like this. If this is process 0, this is process 1, this is process 2, this is process 3, and so on. Process 0 is sending in this order, first to process 1, then to process 2, then to process 3, and so on. So the number of these exchanges will be equal to number of processes. I'll write that as NP, number of processes, minus 1. Later, we will do a more efficient way to communicate between the processes, especially with collective communications. For now, the number of communications between the processes is number of processes minus one. For example, if there were 4 like this, then there will be three exchanges, 3 sends and three receives. Okay, so that was one part. I think I changed code a little bit. I fixed this line. It was just a list. If you remember from yesterday, it was just like this, but it is better, it is smarter to use NP array. Oh, sorry. Okay. This I think I haven't changed at all. Okay. And then after the decomposition, so here what we have the indices where the zeroth process calculated for each of the process what indices it should process. That was like this, or like this in the image. Once it calculated the indices of all processes, it created a smaller chunks of data using those indices. So from main data, the full data, where we have everything, using the indices, we are accessing only the data that process of number I should process, and we are putting that into a chunk. Then if we are the zero process itself, we are just saying my data is equal to chunk, and to everybody else we are sending the data. So this is what process 0 did. Everybody else received the data, and then we can go to parallel processing. In the line 30, everyone has their own data, so all of the processes can summarize their portion. And the processing is quite simple. Everyone should just summarize their elements, the elements or their indices, and then they will have their output in the local sum. So this sum will not be the sum of the all elements in the array. It will be just the sum of these chunks of this my data, which is smaller than the full array. What we should do now is we should summarize all of the local sums. So local sum from 0th process, from 1st process, from 2nd, and so on. How doesn't matter how many we have. So here we decided to send back all local sums to the 0th process. So if we are not the 0th process, we are sending the data, we are sending a local sum to whom this is set by destination. The destination should be set to 0 because we want all the local sums to be at the 0th process. What the 0th process does, it puts its own local sum, so this is the local sum of the 0th process, in total sum at the beginning, and then goes through a loop for all the other processes from 1 until size, until the number of processes, and from each of them it is receiving their own local sum. Here this is set by local sum mother. I changed it to because it's clear. The other thing that I should note here is that this, maybe it seems a little bit weird, but this is a 0-dimensional array. In a NumPy array, if you specify something like this, 0, then it is a without brackets or anything. Then this is a 0-dimensional array where you can put a single element. Okay, and this will be the local sum from other process ones, we receive it. Who is the source? The ith process, process number 1, process number 2, and so on until the end, until the number of processes. Each time when we receive their local sum, we are adding that local sum to a total sum. And let's run this. Should we do? We should activate HPC, so the environment that we created yesterday. Then my file is here. You can see the path, I think, right over there, and it is called first program. So it should be run with npi exec -np. Yesterday I executed it with -n, and it worked on another computer, but here it should be np. So if you're having any issues when you run npi exec -n, just try -np. This np stands for number of processes. Okay, then we will say, let's say just one process, and we are running our code. Okay, and so the sum is 24. We can check it. I think it is. 7, yeah, it's 24. Okay, now we can run with 2. Of course, we will get the same results. 4, 5. Yeah. Okay, maybe let's do some printing or debugging. What is hard with parallel computing is that it's usually more difficult to debug a code that is parallel than the one that is written sequential. Here we will only use printing statements in order to see what is happening. There are some environments and code integrators that are enabling, in a way, parallel debugging, but we will not be doing this here. The codes that we are writing are relatively simple, so the printing statements should be enough. Let's print hello from everybody. Hello. Hello from process and then rank. Okay. Then we can print, let's say, local chunks to see how I am process number and my chunk is that's in my data, right? We could also print a local sum after this. My local sum is, and with zeroth process, maybe we can track all this aggregation. Here I will call the MPI barrier, just in case. It is, of course, not necessary for this code to work, but oh no, that relates to that one, sorry. It's okay. I shouldn't use barrier. Nice. Okay. Hopefully I didn't make too many mistakes. We will see. It works. So it says hello from process number 0. I'm process number 0 and my chunk is like this. It's a full array. My local sum is 24 and when I accumulate sums I get 24. Okay. If we say 2, then it has something like this. Hello from process number 1. It printed before process number 0. That's okay. And process number 1 and my chunk is 2 and 6. This 0 is neutral for addition. So 2 and 6, since we are using cyclic decomposition, are used by process number 1, and all the other elements, so 1, 4, and 11, are with the zeroth process. So the one process says my local sum is 8. That's okay. That's this one. The other says my local sum is 16. That's for this one. And then the zeroth process is accumulating the sums. So at first he has 16. Then he's asking the first process to send him its own sum, which is 8. And then 16 plus 8 is equal to 24. And final sum is 24. Okay, let's try with 3. Now the process number 1 has 2 and 11. The process number 2 has 4, element 4, and 0, non-existing element 4. The process number 0 has everything else, so it starts here. It has 1 and 6. Everyone is printing their own local sum. So this one is 13, this one is 4, this one is 7. And then the zeroth process, it has initially sum 7. Then it receives from process number 1 the number 13. When we add 13 to 7, we get 20. And finally, when we add this local sum 4 to 20, we have 24. And that's it. That is our final result. Maybe I should zoom out a little bit so you can see all of the printing statements in code while looking at the output. I think you can see this clearly enough. If not, please tell me. If we say 5, it will not be very interesting because everyone will have just one element. But okay, we can look at that too. We are process number 2, and our chunk is element 4. 0th, 1st, 2nd. We are process number 4 and our chunk is element 11. We are process number 0, our chunk is 2, and so on. So everyone has very simple sum of just one element. The process 0 has element 1, so his local sum is 1. Then it is accumulating 1 plus 2 is equal to 3, then plus 4 is equal to 7, then plus 6 is equal to 13, and then plus 11 is equal to 2024. Okay. We could also try measuring time. So maybe something like this. Start is MPI dot, I think it's written like this all time. we'll check. This is the time at which our program started. And what we should also do is measure the time when it ended. This is end. And then we could print time of execution is and minus start. Let's see if this works. Okay. So we are getting the time in seconds. And we can check whether we are making this program slower or faster. We're having a lot of printing statements though. So here, with one process, we have something like this. So a point, 3 zeros, and then 4. And for two processes, which we are expecting maybe to be faster, it's actually slower. If you remember, I explained why, because we have very little data. We have, this is our data. This is very, very small. So this will be done on a single process much faster. We are just losing time to create more processes and to communicate between them for such a small task. What we can try to enlarge this. I don't know if you remember, or maybe I don't know if I have shown you, but if you multiply a list by a number, let's say 4, then it is not that each element is multiplied by 4. The list itself is duplicated, let's say 4 times. So maybe we can try something like this here. Let's say we want this to be like this, but I don't think we'll be able to print. Let's try. Let's try. Then we will remove the printing statements. Let's try to see just what happens. Oh. Second, yeah, that's the one. It seems it's not working with NumPy, maybe like this. Okay. Let's check. Yeah, it's not duplicating it, so okay, we'll create a larger list in some other example. Let's not waste time here for now. Oh, okay. This should work. Just a second. So what we used here is a point-to-point communication where we had the send and receive. Okay. So these are the arguments of a send and receive functions. These are the blocking ones. When we are writing the object which we are sending, then we should specify the destination, and optionally we could specify a tag of a message. This tag can be useful if we are sending multiple messages one after another, and we want to additionally specify to make a distinction more easily between these messages. So multiple sends and multiple receives. Then maybe on the other end, of course, the tags needs to match. If you are sending the message with tag number 10, then a receive function should expect a message with tag number 10. If it says 0, then let's say if you put 10 here, and then everything, or maybe better, let's say here, 10 here, and 0 here, it will not work. It won't receive that message. It is expecting another message, a message with tag 10. Okay, these are the non-blocking send and receive calls. We might do them later, not today for sure. Maybe in our last classes, or we'll see. They are denoted as I send and I receive. But when would you use this? When you know that you will need some data and you can ask for them in advance, and then you maybe perform something else, and then ask whether the data arrived or not, or what happened. If it arrived, then you process the data, or maybe you do something else again, or something like that. Okay. Maybe also to note, when you're sending the NumPy buffer, you could use this kind of data. You could specify the array itself, the number of elements within an array, and also their data type. So it is not the same if you're sending in a list of or an array of integers, or you're sending an array of double precision values, or an array of floating point numbers, and so on. So sometimes it is good. It is necessary to specify the data type that you're sending, especially maybe if you're creating your own data type, which consists of several different data types, then you should specify that too. And this is an example with a dictionary. I think we haven't gone through dictionaries sequentially yesterday. We skipped that. So maybe from this, let's take a step back and then come to this slide and see what happens. Dictionaries, I don't know if you have seen them. Maybe you have in some other courses, but they are fairly simple. This is how you create an empty dictionary. If you are asking Python to provide you with a type of this variable, it will output the dict, so the dictionary. And what you're usually using in a dictionary is that you're having a pairs of keys and their values. Here, they were trying to be a little bit funny, and they said key is key and the value is the word value. So when you're asking for key within dictionary, it will output the value. You can also put something like this. So practically anything. You can make a mixture of your data types. You can make a mixture of numbers, strings, Boolean types, and so on. And you can also have a mixture of keys. So any key that you would like to use, you can use. I mean, not well, any, but you can use numbers, you can use strings as keys. And what you store there at that specific key is up to you. So it can be numbers, it can be booleans, it can be also strings. If you're accessing only the keys, you will get keys 1, 4, test, and 7, and also key which we had here. So we added multiple keys. First key was key, then second key was 1, then 4, test 7, and so on. And if you only are interested in values, you can get them like this. So the dictionary dot values, and then the Python will output all of the values that you stored. If you want a value under a specific key, you just say the name of your dictionary, and then in squared brackets, you specify the name of key, and it will output a value. Then you can create a dictionary like this. So these are the keys A, B, C, D, and these are the values 1, 2, 3, 4 behind those keys. So those are the dictionaries, and then we go back to an NPI example. What has been done here is, this is like a standard program. We specified the communicator in which all of the NPI processes exist. We got the ranks and the number of processes. So this is like the process identifier. Your 0th process, your 1st process, and so on. And this is the total number of processes. If we are the 0th process, then we are creating this dictionary, which has 3 keys: day, age, and z. And the values are Monday, 20, and this list of 3 elements, 93, and 1. And once again, we are using point-to-point communication. So we are sending the data to everyone else. How we are sending the data to everyone else? When we are going through a loop in which we are starting from a first process all the way up to the number of processes, and to each of them we are sending this data. We are sending the dictionary. To whom? We are sending the dictionary to the ith process this, and then we are also specifying the tag. So the default value for tag is 0. For here, it's not necessary, but if you are specifying tag here, then you must specify a tag in the receive end. So this has been done by a 0th process. By everyone else, no matter how many processes we have, this will be executed. So it will receive from the source is from whom you're receiving, and this is tag, and it will return a dictionary as a return. So it sometimes in conreceive you can com.receive, you can specify a buffer in which you will store the data, but if you do not specify the buffer, it will return the data like this. And then you have the output, second and first process printed what dictionary they received from A. Of course, it will be this dictionary. We didn't print from process 0 because that's already here. We could add printing statement here if we wanted. Okay. Then the other example is to send an array. So this was how you would send a dictionary. This is how you would send a NumPy array. So the process with rank 0 is creating an array with values from 0 all the way up to 10, but not including 10. So values between 0 and 9. Their type is integer. I'm not sure if in all version of Python this will work. If it doesn't, well, let's try this. Then we can change code. I will just replace all of this because we already have the first program. Oof, this is not great. need to fix this a little bit. If we are rank 0, then we are creating an array with elements, since this is a range function, and with a single argument, so it will only create elements between 0 and 10, not including 10. And then we will go in a loop through all processes and send to each of them an array. So what we are sending, we are sending an array A with 10 elements, each of them being npi int. So this means integer. Why do we specify int and not npi int? I mean the other way around. Why did we specify npi.int and not just int? That's because this could work in an environment where we have multiple processors, and one processor could have its integers written in 4 bytes, the other might write them in 2. So it is a good practice to, I mean, that's really rare, but just in case, to be careful, you should specify npi.int and then you're safe. This is this will be unique among processors. So this is what we are sending. We are sending an array A of 10 elements, with each being npi integer. Who is the destination? Similarly as before, the destination is the ith process, and we decided to use tag 7. Okay, then if we are not 0th process, so if we are everybody else, we just, let's say, reserve the data for 10 elements. They're all zeros at the beginning. And then we call the receive function. We say we will receive this data into our myA function. We will receive 10 elements. Each of them will be npi int. We are receiving this data from source 0, and the tag is 10. Then we should print. I think that this is an older version of Python, so it might not work, but let me try. Oh, it works actually. It works perfectly. Great. So what is happening? The 0th process created this array. If we run 2 processes, the 0 created one array, and the process number 1 received that same array. If we created 3 processes, then once again the 0th process created the array, and the other 2, the processes number 1 and 2, just received that array and printed it on screen. Let's try 13. So this is what we get. You see here that printing doesn't necessarily come into some specific order. So you see the first one printed here. What actually happens? The process 0 is sending the data from first process to the last process. They're receiving it here. So the first process comes to this line, then comes to this line and waits. When it receives the data, it can continue and print. Sometimes it can reach this function, this line, later than, let's say, second process, then third process, and so on. Okay. It is up to us to write such code that it does not matter in which order the processes are getting their time on processor, their execution time. But of course, we can use NPI barriers If we want to synchronize them, we can use send and receive if we want to exchange communication in a point-to-point manner. So send and receive is always between two processes. One is sending, the other is receiving. If we want to send the data to multiple processes, this is what we are doing. We are going through a loop from the processes, and we are specifying the processes that we want to send the data to. So it's everyone from the first to the last process, and we are sending. Here we are receiving everybody is receiving from zeroth process. So we only have this one line here, and here these two are important. Okay. We can also send one number. That's okay too. For example, if you want to send the partial sum, like we did before, this is a sum of first 100 elements. It is not a very smart code. I will explain why. So what has been done here, we want to summarize all the elements from 1 or from 0, whatever, until 100. Then we divided this domain, this 100, into portions by using this formula. So this is my rank, and it will be 0 for the zeroth process, 1 for the first process, and so on. We are multiplying that by n and then dividing by the number of processes and adding one just in case. So this will be the starting point from which the process should start its summation, and this will be the ending number at which the process should run its summation. And this is domain decomposition. So not the one that we did with our summation. The one that we did with our summation was cyclic decomposition. This is a domain decomposition where we are using the formulas to, and you can use these formulas almost always. There are some more advanced, which we will see maybe later today, maybe in another week. But here with domain decomposition, we are deciding what portion of an array is prescribed to each of the processes by using these formulas. So at what index the process starts, or at what number, and at what number the process ends its summation in this case. And the formulas will always include, of course, my rank, the rank of the process itself or its ID. It will include the total number of values, and it will include the total number of processes. The easiest possible way to delete this to make a domain decomposition is when we have numbers like this, I don't know, 100 elements, and we have, let's say, 5 processes. So 1000 is divisible by 5, and we can have 200 elements. Just let me 1, 2. It doesn't seem equal in my image, but I think you will get the gist. So the 0th process is doing 200, first process is doing 200, second process is doing 200, third and fourth. So everybody is doing the same amount. But if you have here, I don't know, 6 or something like that, you have to be careful to divide this among five processes in a fair way. You shouldn't let everyone do 200 elements and then one of them 206. No, you should divide these 6 almost equally. So you will have them all do 200 and maybe just the last one 200, 202. I think that's okay. 1, 2, 3, 4. Okay, yeah, something like that. So this is what the formulas take into account. They take this case where you have where your number of elements or tasks is not divisible by a number of processes that you have, and you don't know in advance how many processes someone will start. He might start 2, he might start 5. So you will eventually get a case where the number of data is not divisible by your number of processes. Okay, sorry. So these formulas take that into account, and you will you can be sure that the load balancing or that the data will be almost equally distributed along the processes. Then we are creating a zero-dimensional array for partial sum, and everyone is adding the numbers from their start of the interval until the end of the interval, including the end of the interval. They are adding their own numbers, and once they added their own numbers, then we perform the same task that we did before. If we are not zeroed process, we are sending our partial sum, but here they are sent as an NumPy array. So we are specifying what we are sending. We are sending just one value, just one element, and it is of type NPI integer. On the other hand, if we are the zeroed process, we should accumulate all of these sums. So similarly as what we did before, we create a zero-dimensional array. We are asking from everybody else to send us their partial sums. So we are receiving the temporary sum of the process in the index I. We're receiving just one value. That value is of type NPI integer. That, of course, matches the one that is being sent. And once we received the partial sum, we add it to this our partial sum. Okay, and we will have a total sum once this loop finishes. Once this for command finishes, we have the total sum of all numbers. Why I said this is not a smart way to write a program, because this can be done very easily mathematically. When you need to summarize the numbers from 1 until 1000 or 100 or whichever, you can use a simple formula, and it's not part of this course, but maybe you should know about it. This is like a very busy way to do this. If somebody asks you on a paper to summarize all of these numbers, there's a smarter way to do it. Because 1 plus 100 is equal to 101. 2 plus 99 is also equal to 101. 3 and 28 also. You're noticing probably the pattern. So when we are adding the numbers at the ends of the intervals, we will always get this. And how many summation of these we have? We have until we reach half of this array, okay? In this case, it will be 50. So it will be 50 times 101. In general case, the formula is, so this is actually n plus 1. This is what we see here. When we add 1 and 100, if this is equal to n, then we have this. And how many of these we have? Well, we have n divided by 2 of these numbers. So this could be a practically single line program where you just, or you can even write it like this, which I prefer. You could just write this and calculate the sum. So, but this could be a good way to practice a send and receive functions. Okay. Are there any questions for point-to-point communication? We have seen here I haven't checked the chat, but I think they are not. Yeah, I think no questions. What we have seen is we have seen the cyclic decomposition, we have seen the domain decomposition of data, and now we'll see one specific way to calculate a pi value, in which we will not be needing neither domain decomposition or cyclic decomposition. It can be considered a way of domain decomposition, but actually each of the processes will have their own data, their own generated data. So no decomposition of initial data is needed here. And this is the assignment. So Monte Carlo's method for calculating pi. It is a bit mathematical, but not too much. Let's draw. This is what they sometimes call, embarrassingly, parallel programs. This. So we have here is, oh, it's not a circle. Okay, I think it's approximate enough. So what you probably know from mathematics, it's that the area of this circle is r squared times pi, right? If we set r to 1, then we will have 1 times pi, right? So we'll just have pi. Okay. Then Monte Carlo method says something like this. So this is 1 here, and of course this 2. This is, and then we have this square. And then within this square, we can just randomly put points. Some of the points will be inside the circle, so within this square. Let's make it like this, within this square. We will randomly generate values. Some are inside, and some are outside of the circle, but they are all inside of the square. Okay, and what we can do, we should generate as many points as we can. What we should do is we should count the number of points that are inside, and if we divide that by total number of points, so number of points inside, I'll just put in, divided by total number of points, we will actually get a portion of this surface relative to the square. So we will get 1/4 of circles surface, right? And if we have 1/4 of circle's surface, then we are actually having pi over 4. Okay. What we can do, we can actually, if we multiply this by 4, then we are getting the pi value. And what is the goal here? The goal here, we already know pi, right? 3.14, but we want to get as many decimals as possible. And here we will see that once we have more points generated, we will have a more precise pi value. This could be performed, of course, sequentially. You just generate random values between 0 and 1, check whether they're inside circle. You can check whether they're inside the circle if their coordinate, x coordinate, and their y coordinate is less or equal than 1. The summation of this. Why? Because if you remember mathematics, the equation of this circle is x squared plus r squared is equal to y squared is equal to 1 in this case because r is 1. You can check the equation for circle. It is actually a little bit more complicated. It is x minus center x squared plus y minus center y squared is equal to r squared. That's the full formula. But our center is at 0, 0, so this can be deleted, and our r is 1. So this is like a simplified equation for our circle. Okay, so we're writing a relatively simple program. We are generating two random values, one for x coordinate, the other for y coordinate. Both of these values should be between 0 and 1. Then we add their squares together and check if they are less or equal than 1. If they are less or equal than 1, then the point is inside. Otherwise, the point is outside of the circle. We do this many times. Many times we generate a new point. We check whether it is inside or outside. And finally, once we are done generating all the points, we just calculate its value. We calculate the ratio of points that are inside regarding to the total number of points. We multiply it by 4, and then we get our pi value. So I'll show you code, parallel coordinating. And how would we parallelize this? So each process themselves can generate their own random values. That's important. There is no data dependency here. There is one thing that is needed, and it is needed to make sure that values that are being generated are as distinct as possible. So each process should have their own seed value. I will explain what that is. Let's look into the code. Just let me find it. And that's this one. It should work. I'm calling everything first program, even though it's not first program. But okay. And let's try this if it works. This number is way too large, so I will lower it to let's say 100. I'll explain about it. This is the number of points. This is the number of points that we are trying to generate within a circle. And this is a pi value with 25 digits. So this is the accuracy of that. We will not, of course, not achieve 25 digit precision with just 100 points. No chance. But let's try just to see if it works. Okay, so as you can see here, the pi value that we got is not correct. It's 3.13, and you see here the elapsed time that we needed to get this. But if we increase the number of points, let's say 10,000, then we are getting closer, still not close. If we say 1 million, I think this is 1 million, right? Yeah. Then it's still not precise enough. It depends a little bit even on the points generated, of course. But in general, as we increase the number of points, the value should be more precise. Okay, this one is better. You see, it's 3.14159, and we got 3.1414. Closer than this, for example, or than this, or than this. Okay, let's see the program. So in standard way, we get the communicator, we get the process rank, we get the number of processes, and if we are the 0th process, we are just measuring time. This minus sign shouldn't confuse you. You could use just this. So this is the current time of the program. And then we have this seed. What is seed? Seed is used to generate random values. None of the algorithms are actually capable to perform really random values. All of the algorithms are pseudo random algorithms, and they require some starting value based on which they will generate the random data. And this is the seed value. This seed value could be anything. It is usually the current time is used. And this is used here like this. But theoretically, all of our processes, we can start multiple, let's say 2. It might happen that both of them reach this line at the same time, and then they will generate the same numbers, which is not beneficial at all. We need 2 processes to generate different values. And so somehow we should involve their ID in order for them to get different values. Okay, so here it is decided to multiply. No reason to multiply. You can add, you can do whatever you like. You just need to include somehow the process's ID into the formula, and this should be included. The idea process should be part of seed value when you are writing the parallel program, okay, to generate random values. In sequential coding, this ID does not exist, so you would use maybe something like this, but in parallel programming, it is necessary to include ID in some manner. You could even just use the ID, that's okay too, but since IDs are fixed, your program will always produce the same values no matter how many times you run it. If you're okay with it, sometimes that can be good, especially when you want to repeat the experiment. It is good to have the referent, let's say, seed value. But you could use something like this. Okay, so this is just setting the first value, the initial value for a random number generator. And then we are doing what we said we will do. Each of the processes is doing A divided by the number of processes. The A, if you remember, is this large number in the beginning. So this is the total number of processes, the total number of points. And we want all of the processes to generate the number of points that is equal to A divided by the number of processes. So if we are having 2 and we have 1 million here, then one process would generate 500,000 and the other would generate also 500,000. In total, that will be 1 million. If we are having 5, then each will generate their own portion of points. Here we do not care that much about the remainders and the division. So if it is 1 million or 1,000,006 generated points, we don't really care if we don't generate few points, because a very large number of points is needed to get the accurate precision of our result, in this case the number of pi. Okay, so here we do not care about remainders or whether there are any. This variable will serve as just to count whether the point is inside or not, and then we are generating a random value between 0 and 1 for x coordinate. We are generating a random value between 0 and 1 for y coordinate, and if the x squared plus y squared is less or equal than 1, we are saying that this point is inside. And we performed all of the necessary calculations here. Now, each of the processes have their own inside count. So one process could have, I don't know, 300, the other could have 700 points inside, and so on. So we should merge all of this together. We should add all of this together, and we already we saw that before. So we are not the zeroth process. We are sending our in count, the points that we counted that are inside. And if we are the zeroth process, we are performing the other calculations. So we will have the total number of points that are inside. We will ask for all other processes. So we are going in a loop for all other processes, starting from 1 until the end. And then we are receiving from the ith process their inside value in this way. And then we are adding that to our total count. So in the beginning, our total count is our value as a zeroth process. And then for all the other processes, we are receiving their value, and we are using their value to add to the total. Okay. So that's about it. This is just printing how much pi is. So how much pi is? It's total count of the points that are inside divided by A, which is a total points that are generated. So some of the points, if you remember, are inside the circle. Some of the points are outside of the circle. I will remind you once again using this image. So some are inside and some are here outside. This is a total number. This is a number of points inside. If we multiply that by 4, we get the pi, and then we just print everything. I changed the sign here in the beginning. I prefer to use something like this, start time. This is okay too. I think I will upload it. But, and say this is the ending time. And then elapsed time is starting time, is ending time. Minus star. Here, what was done, the minus sign was written here, and the plus sign was written here. It is the same thing. Okay, what we are printing our pi value. That's the obtained value. And we are printing the difference between the 25 digit precision pi value and our acquired pi value. Okay, and let's check the program once again. Let's do 10 million points. And let's do 2 processes. We might wait for 1 second time. And then we will try the same thing. Maybe we can do it right away. Okay. With 4 processes. And we should check if we are faster or slower. HPC, desktop, it's NPM. Okay. So I'm running the same program, but with 4 processes. All right. Oh, we got an seed error. That happens from time to time, depending on the time. This value could be wrong. So, like I said, you could change this to just ID. Let's do that. Sometimes it works, but sometimes it can lead to an error. Let's delete it. I will break this. I think it's very slow when it's 2. Let's try 4. And maybe if we are waiting for too long, then we will. I'm thinking because I do not have many cores on this processor. So I'm thinking how many processes to start. I don't want to overwork my laptop. Just a second, excuse me. Is it not what I wanted? I do have 4 cores, so no more than 4 is smart. Okay, let this work in a background. I haven't explained exactly this MPI finalize function. That is the last function that should be called. If you don't call it in Python, it is not dangerous. But if you were programming in C and if you do not call MPI finalize, okay, so sorry about that. My battery died. I forgot to plug my laptop in. So where was I? I think I was talking about MPI finalize. MPI finalize is necessary in C. In Python, I think it takes care of itself if you haven't written it. But in C, if you don't write the MPI finalize, it will lead to an error. It will be an error at the end of your program, so after everything uh, has been performed, but still it is good to have it. So it actually gets rid of all of the MPI structures. And after that, after MPI finalize, you can't call any of the MPI functions within your program. So you can only once you start and once you call the finalize, after that you cannot restart and do the MPI functions again. It will lead to an error. Okay, so is my program still running here? That's the main question. It's finished. It finished, so this is the precision that we got, and this is the elapsed time, so almost 2 minutes. And maybe if we run it with 2 and wait, see what happens. I am expecting the 4 to be faster, but it doesn't always have to be the case. It really depends on the number of data points that we are having. It is when you write a program and when you know the amount of data that you want to process, it is a good idea to start it with, well, it really depends how huge, how large your data set is, but I usually run some tests and run on the create 2 processes, create 5, create 10, maybe create 100 if it's really huge, and then I check which number is optimal here. Our goal is to make the program run faster, especially when we have a lot of data. So this is, I think, the ending of a point-to-point communication. All of these programs that we wrote with point-to-point communication can be implemented more efficiently using a collective communication. The we will try to improve this Monte Carlo's method with collective communications. Let me do this. Okay, so in this case, actually, what was faster with 2, and if we say with 1, maybe with 1 it will be slower than 2, but faster than 4. We don't know yet until we check. The number that is written in the file that I will provide you with, so not this one written in the first program, but actually the one that I will upload here is quite large. If you run it on your computer, make sure that you lower it first. Maybe try something simple, maybe with I don't know, 100 points. That's fairly small amount, and it will finish very fast. For experimentation, you can wait if you want. It will finish eventually. Okay, let's go to the collective communication. Let's say you are reading a single value and you want to send this value to all of the processes. Your process 0, your reading value n, and you want to send this number to everyone else. I think that's enough. Process 1, process 2, process 3, process 4. Here we have a total of 5 processes. A little bit of convenient, but okay. What we learned so far is write send function and send the number to P1. Then send the number to P2. Then send the number to P3. And finally send the number to P4. So we have 4 exchanges. Can this be more efficient? We are waiting for the programs to send the data and to receive the data. Not programs, processes actually. Okay. What can we do? If we send in the first step our data to process 1, then there are 2 processes that know this data. They can both at the same time send them to somebody else. Let's say to P3 and P2, these 2 can perform simultaneously at the same time. And then finally, all of these 4 processes have the value. One of them, doesn't matter which one, but it will be this one, will send the data to P4, right? So if we had communication like before, where we send single data to all of the processes, the number of sends and receives or exchanges was np minus 1, where np is the number of processes. Here we have something a little bit smarter. Here we have, if we have 4 processes, so look just at this portion. In this linear case, we would have 3 sends, but here, as you see, we have 2. What would happen if we had, for example, 8 processes? 0th process, first process, second, third, fourth, fifth, sixth, and let's say 7. So in this manner, we should send to everyone and receive from everyone. We would have 7 exchanges, right? NP minus 1. So if we have 8 processes, there will be 7 exchanges, 7 sends and 7 receives. But if we implement something like this, so P0 sends the data to P1, and now they both have this data. Then this is first step. Then at the same time, so the number of sends and receives that are performing at the same time will increase. The sending between process 0 and process 1 to process 3 is performed at the same time. So process 0 has the data, process 1 has the data, and they can both at the same time send data to processes P and 3. And now 4 of the processes have the necessary data, and they can all together in a third step send the data to, this is a number 3, send the data to everybody else. So in this case, this is actually the logarithmic efficiency. It is a log of base 2 for NP. I don't know how much you remember mathematics, but if you have 8 processes, so logarithm of 8 would be 3. 2 to the power of 3 is 8. Of course, if you have one less process, so it's still going to round up to 3. So, and this has already been implemented in function. We could implement it ourselves with send and receive. It is not very difficult, but there are already built-in functions. For example, what I have described here is that one process 0, sends the data to everybody else. That's the communication called broadcast. In broadcast, we're just specifying from whom we are sending the data. For example, from process 0. It doesn't have to be process 0, it can be somebody else, but we are sending a data to everybody else. So this is broadcast. I think I have some. Yeah. So process 0 has the data. And then if it broadcasts, everybody else will also have this data A. This could be one single element, this could be one array, or whatever. And this is the notation you see, so you don't have to look through that. I mean, it's not very difficult, maybe just short. You have the buffer will what data you're sending, and the other will be received. Will receive the data in the same buffer. So the process that is sending has the data here, and the processes that are receiving the data will receive the data here. Okay, in the same variable, let's say. This is the same variable in a sense that it will it doesn't necessarily have to have even the same name on the different processes. It just has to be it just has to have enough space to receive the data. Then we have how much data we are receiving. So this is a buffer. Then we have how much data, and then data type. So MPI int, MPI float, MPI double, whichever. Then from whom we are sending to everybody else. This is usually a 0. And then the communicator in which we are communicating. The Python function is actually a bit simpler than this. We will see it later, but this is the case of broadcast. So the broadcast we will use when we have the data. For example, initial data, we read it from process 0 and we want to send it to everybody else. Then we perform broadcast. Then we have MPI reduce. And this reduce is used when we have partial results, which we had before. We had partial results in our first assignment where we did the summation. We had the partial results in our Monte Carlo's program for calculating the pi value. And from those partial results, we want to somehow aggregate them to reduce them to a single value. Maybe we want to summarize them. Maybe we want to find the largest value. Maybe we want to find the smallest value. Maybe we want to perform some operation. Maybe some of their absolute values. Maybe we want to perform some of the logical operators on all of these values. So in any way, when we have partial results and we want to obtain one single result from those partial results among processors, we will be using MPI reduce. Sometimes it will need a little tweaking depending on what we do, but if we need sum, max, min, and so on, that's already built in. So we can use that. And this is how it works. So all of the processes have their values, partial values. We make some kind of aggregation, so summarize them, find the largest value, and so on, and then send this to one process. For example, process 0. We have been doing this with Monte Carlo here. But this is not a very smart way to do it. We are sending the partial data, and zeroth process is summarizing, receiving the data from everybody and summarizing it. Reduce is written in a smart manner, similarly to how the broadcast was implemented. So like this, with more efficient communication, where only where not np minus n steps are for communication are needed, where we have a logarithmic efficiency of communication. Reduce was written in a similar manner, but here I will try to make a sketch with 4 processes. So this is process number 0. This is process 1, process 2, process 3. They're all working together, and they have, let's say, partial sums. So process 1 can send its partial sum to process 1. At the same time, process 3 can send its partial sum to process 2. So this happens in one step at the same time. And then finally, so process 2 will have its own partial sum and partial sum of P3. So it can summarize those two together. So now he has those two together. And P0 has these two together. If process 2 sends the data to process 0, that will be a second step, then P0 can summarize everything and we have final value. I made this too messy, so I will explain once again. Process 0, process 1, process 2, and process 3. So at the same time, these are sending their partial data, and processes P0 and P2 are calculating this partial data. So process 0 will have, for example, partial sum of its own sum of P0 and of P1. It will add them together. P2 has its own partial sum and has the sum of partial sum of P3, and it will add them together. This happens in a first step of communication. And in a second, and in this case, final step of communication, the process 2 sends the data to process 0, and process 0 will have the final summation. This is just like a behind of MPI reduce what is happening. How does the function look like? It has what we are sending. It could be a single value, for example, partial sum. Then we have what we are receiving, where will be the final result. So this will be the partial sums, and this will be the final sum. This does not have to be a single value. We can perform a summation of a vector or of anything. But for simplicity, let's say single value, then we have count. So 1 if it's single value, then of which type the data is, what operation are we performing. And these are some of the available operations. Max, min, sum, product, AND, logical AND, logical OR, and logical XOR, and so on. Binary AND, bitwise actually. Okay, so that's the reduction operation. Then we have the process that is receiving the results and communicator. So only the one in this MPI reduce, only one process will have the total summation. In our sketch, that was the process 0. Process 0 had the final value, and all of the others had some partial result. Okay. Let's check collective communications in Python with concrete examples. So here, if you remember this example from before, this was domain decomposition, and everybody already had this n. Everybody has the n. If only one process had n, what we could do, we could broadcast it, but okay, we don't have that here. Everybody knows n. Everybody has their starting value, their ending value, and they should summarize everything in between. Once the process is summarized, what we should do here is everybody has some portion of a total result. We should reduce this portion, or we should aggregate it or call it wherever we want, into a single value and have the total sum. So what we have here is what we are sending. We are sending a partial sum that is a single value that is of type integer. We will have our final result in a total sum. It will be a single value. It is of MPI integer. What we are performing the sum, and who will have the final data. The final total sum will be at the process with rank 0. So this should be anyone from 0 until a number of processes -1, but usually this could be, but usually it is the 0th process. There is another function that is called reduce all, and it is the same as reduce, but it is missing this root is equal to 0. Why? Because reduce all, this all at the beginning, practically means reduce plus broadcast. Reduce to somebody, doesn't matter who, and then send back this final data to everybody. Okay, that's reduce all. Maybe we will have the example. If not, try to remember it. So it's reduce all. And it is the same as performing reduce and then broadcast from that process that has the total sum. Okay. This is scatter. What does scatter do? With scatter, I'm not sure if I have it here. No, that's probably in some other presentation. But with scatter, maybe I could try and find it because I have, oh, just a second. I think I can find it fast. My voice could also break, so that's fine too. One more minute. Yeah, I have that. Okay, gather function or gather scatter. What is scatter function? Scatter function we have some data, for example, let's say an array of elements, A, B, C, D, and we want to equally distribute them among the processes. So if we have ABC and if we perform a scatter, then this data will be distributed among processes. So at process 0, we will have A. We will not lose this data A, B, C, D. They will still be at process 0, but in another location. At process 0, we will have A. At process 1, we will have B. At process 2, C, and then D. This A, B, C, D does not have to be a single element. It could be, let's say, 5. 5 elements here, 5 here, 5 here, 5 here. But with scatter, it should be the same amount. There are other function. There is other function called scatter V. We won't be doing that one today, but scatter we can distribute the values unequally, but a lot of specification have to be done in that case. And this is a C representation. I will explain it shortly. So this is what we are sending, A, B, C, D. This is how many there are. Maybe there are 10 values. This is a sending type. Then we have what we are receiving. So maybe we're receiving A, maybe we're receiving B. How many values we are receiving? What is receiving type? Usually these two types are the same. I don't think I have found a single example where they haven't been, but maybe. In my experience, they should be always the same. Then we have rank. This rank is from whom we are scattering. Who is the initial process, and this is the communicator at which the communication is performed. So A, B, C, D, from whom we are scattering from 0th process to everybody else. In Python, I don't think communicator is necessary to be an argument of a function, because if it's omitted, then it is assumed that we are working in that COM world, in the communicator that has all of the processes combined. Okay, so that's scatter. and this is the example. So we're having some data, 23 AB, and this here. And in Python, this example is really simplified because we have this dictionary, which will be distributed along the three processes. So 23 will be at the 0th process, the AB will be at the first process, and this list will be at the last process. So this is the result. The full data is at 0th process. First process has AB, of course. 0th process has 23, and second process has this set and set Z and 22. Okay, so this is the scatter function. This is the full data, and this is from whom we are scattering the data, and the result will be in my data. So full data, this is a full array, then from whom we are scattering, and everything else will be in my data. This won't work with, so this is a very basic example, and it will not work if the number of processes is not 3. This will break. That's why the assertion was checked here. Okay. Now we have a scatter once again, but written in a little bit better way. We have full data, which are the data from 0 until 9, but not including 9. So from 0 until 8. And only the 0th process has them. Then we want to scatter this data from 0 until 9 among other processes. Everyone will have three data. So the 0th process should have this, 0, 1, 2. Second process should have 3, 4, 5. And last process, 0th, first, and second process will have 6, 7, 8. So this is what we are trying to achieve. And how are we doing this? This my data is only used as a storage where we will save these 3 variables. Then we are performing the scattering. From whom we are performing the scattering? From process 0. What data are we scattering? This one. So we are scattering full data. It has with MPI int, and we are receiving the data in my data. It is also of type MPI int. Both of these are 3, but this actually means 3 times the number of processes, and this is 3 just like I want to receive 3 values. Let's try this. Should work. Once again, I will write it in my first program. You can try it in some other file. Just don't forget to replace the name of the file when you're writing the command. So it is MPI exec -np, the number of processes, then Python, and then the number of Python file. Just let me fix this. We're using the if we are the 0th process, we are creating the full array. We are printing the data. Then at everybody else, we don't have the data. Then after that, this is performed by everybody. Okay, let's try. So it should be run with 3 processes, or else it won't work. And this is what we get. So it works. The 0th process has 0, 1, and 2. The second process, or the last one, has 3 final values, and 3 values in the middle are given to the process 1. This is all, of course, in my data. In full data, only process 0 has everything, and all the others have this none, empty data. Okay, so that's scatter. I think we're halfway for today. I think we can skip this implementation of communication ring. Is it okay if we take a small break for, let's say, 5 to 10 minutes? I think somebody has some question. That was like in the beginning. So we'll have like 5-minute break, maybe 10, and then I will come back. maybe we can continue. I'm not sure if this second session has been recorded. Maybe I can press record. Oh no, it says it's recording. Okay, I think that's fine. So let's continue. Where have we? This is just like a summation of all of the collective communication functions. So the first one is MPI broadcast, where a single process, in this case process 1, has the value. This could be an array. It doesn't have to be a single value. It can be a vector or anything. And then we are sending the data to everybody else. Scatter, we have usually a vector of data, and then we are sending portions of that vector to all of the other processes. So this is what we are sending. This is what we have before, and this is what we have when we receive. Once again, this does not have to be a single value. It can be multiple values, as you saw in the previous example. Then we have getter. Getter, I don't know if I explained it. I think I haven't. This is getter. So how getter works? We have portions of a vector on all processes, and we want to make a whole vector out of those. So everybody has their own data, their own A, let's say, and once we do gather, these are collected in a vectorized manner. So we will have data from process 0, data from process 1, data from process 2, and data from process 3. And they will be collected here within the root process. In this case, that's the process 0. This is how gather works. We have what we are sending, how many of the data we are sending, which data type. It's usually, it can be MPI int, MPI float, whatever. Then where we are receiving the data, how many data we're receiving, and the type. These two types usually say they are most probably the same. Then to where the result will be, at whom, which process. And finally the communicator, which is usually omitted because that's the communicator convolved. So here, gather, we have portions of a vector. Once again, this can be multiple values, and we gather them in at a single process to have all portions of a vector have a full vector. Pulp gather is the same as gather and then broadcast. So we collect this 1, 2, 3, 4, and then broadcast to everybody else this data. So this is all gather. We have reduce. For example, here we want to summarize these values. Everyone has their partial value. Once we perform the reduction, the one process we have the reduced or summarized all of these values together. In this case, that is 10. And all reduce, as I mentioned before, is the same as reduce plus broadcast. So this will be computed, this 10, and then it will be distributed amongst the other processes. So everybody will have this data. And you don't need to look at this. All to all is that we send data from all processes to all the other processes. It's sometimes kind of messy. Reduce scatter is combination of reduce scatter MPI scan. Is a function that accumulates values or doesn't have to accumulate, but it performs partial reduction amongst processes. So if we have 1, 2, 3, 4 at the beginning, then we will have 1. Then when we accumulate 1 and 2, we get 3. When we accumulate this 3 and 3, or all the other values here, it's the same thing, we get 6. And finally, when we accumulate 6 and 4, or all the values here, we get 10. So this is what routine scan does. It performs partial reductions. These three functions you don't have to look at, but these reduce, gather, broadcast, and scatter you should take a look at. And so let's try to fix some of the codes that we have written before. Just open the Monte Carlos program, for example. Okay. So where we had point-to-point communication in Monte Carlo, here no communication. We only have the communicator, but that's not it. We have here, right? We have this part where we are gathering the results from all processes, but this don't let this confuse you. This shouldn't be gather. This is actually a reduction. We should summarize all of the partial sums in Monte Carlo. If you remember, our goal was to generate a number of points and to check whether they are inside of the circle or not. If they are inside the circle, then we will use the portion of the points that are inside of the circle and a total number of points, multiply that by 4 and obtain the final pi value. But each of the processes have their own number of points that are inside. Someone has 100, someone has 105, and so on. We should first summarize these points that are inside together, generated by all processes, and then compute the final value. So this summation is done here. If we are not the zeroth process, we are sending our partial number of points to the zeroth process. And if we are a zeroth process, then we are calculating the total amount. Our total amount in the beginning is just the count of points that are inside at our process, at process 0, and then we go from in the loop for everybody else, for all the processes between 1 and a number of processes minus 1, and we are receiving the data from them, and we are adding that partial number to our total count. Okay, so we have partial count from each of the processes, and we are summarizing them. And here I think it is clear that we should use a reduction. We should reduce all of these values to a single sum. We are reducing the partial numbers of points inside the circle to a total number of points inside a circle. And so these lines of code from 29 till 36 can be replaced by a single reduced line. And this we have here. This is it. So all of this has been replaced by a single line. ComReduce, what we are reducing, we are using this partial in count. We are using NPI sum to summarize all of this, and the final result will be at the zero process. So this global int count will be, everybody will have this variable, but only the zeroth process will have a total value inside of this global int count. That's how it is called here. You can name it whatever you like. So this is, once again, a number of points inside the circle for each of the processes. We should summarize all of them by using MPI sum, and this could be at a zero. We could use reduce all here if we want to. Then we should omit this. If we want to have the global sum or global int count in all processes, if we want to have the exact value for all of them. But in this case, it is not necessary, because we are only the zeroth process will be using this value to print the final result. When would we need the reduce all? We would need reduce all if all processes need this value for some of their calculation. This is practically final calculation, so this multiplication should be done only by a single process. We don't need to repeat this many times. Only zeroth process should calculate final value and print it on the screen. Okay, so this has been the collective version of the Monte Carlo function, and as you can see, it is simpler to write this single line than to write all of this. Plus, it is more efficient because behind it is a logarithmic complexity of communication, and behind this is linear complexity of communication, and this is more efficient. This is better. We are processes are communicating with each other, sometimes in parallel. So, for example, process 0 and process 1 can communicate at the same time as process 3 and process 2. That two communications are totally independent of each other, and they can happen at the same time. Here we don't have that. Here every communication is separate. First process 0 communicates with process 1, then process 0 with process 2, and so on. Okay, let's go to another example. And this example is actually maybe a little bit more complicated. And that's why I won't be expecting you to understand much of the details, but I will explain you the main parts. So this is the implementation of sieve of Eratosthenes. This is used to mark all the prime numbers in a list of numbers. So prime numbers are the numbers that are divisible only by themselves and by 1. First prime number is 2, second prime number is 3, then 5, then 7, then 11, then 13, and so on. And our goal is to find all such numbers that are not that are divisible only by themselves and by 1 until a certain value. And here the domain decomposition is used to compute the starting number and the ending number at which the process examines whether the numbers are prime or not. Maybe I can find some animation to show you. I mean, it is a complicated code, so not like for a demonstration. Let me find. Okay, it has one on Wikipedia, so that's kind of good. Let's restart this. Oh. Just a second. It's going way, way too fast. So first prime number is 2, and then it marks all the numbers that are divisible by 2 until the end of the list, so every second number. Then you find a second number that is not marked. And then you mark every third number. Then you find number that is not marked, and then you, let's say, delete every fifth number, in this case, every number that is divisible by 5. Then you find the next prime number, which is 7. Then you delete all the numbers that are divisible by 7, and so on. And you do this until you reach a square root of the final number, and then you're done. Then all of the numbers that are divisible by some numbers are, let's say, deleted or marked, and all of the rest are primes. So primes here are 2, 3, 5, 7, 11, 13, 17. Well, actually, we have them here, 19, and so on. So these are the prime numbers. Numbers that are left that are not divisible by any other number. There are, of course, many other algorithms to calculate the prime numbers, to mark them or whatever. And this one is especially tricky for parallelization. And this parallelization that has been done here is maybe not one of the most efficient ones that I saw, but it is okay. So, but you should maybe pay attention to here. These are the formulas for domain decomposition. So you can use these ones instead of the ones that we saw before, but any are fine. This low plus 1 is to skip the zero value. Then the zeroth process finds the small primes. I don't need you to look into the details of this function. You can if you want and if you would like, but it is not necessary. This part is maybe okay to look at. Just remember, so in this part, the zeroth process finds the small primes. And then these small primes are broadcasted. So this is important. This is MPI function. We are broadcasting these small primes that zeroth process found from the process 0 to everybody else. So everybody will have small primes. And then everybody should mark their portion of the data. You know, no, they don't have the full data. No, not all of the processes or full numbers, full number list. They are only marking their own. And how they are marking? They are going through a list of primes. So they are taking one prime at a time from a list of small primes. And then they are deciding at what line to start. You don't have to look into this formula. And then going from start to their end, which is high, they are taking every prime number. So if prime is 2, they are taking every second number, and they're marking it as false, as not a prime number. So every number that is divisible by 2, except for 2, is not prime number, right? 4, 6, and so on. Then they take second number, the second prime number, which is 3. And then they mark every third number starting from that, that it is not prime, so it's false. And what is left in the end, after this is performed, it is left that everything is true where we have prime numbers, and false is where we don't have prime numbers. What we don't have here is everyone has their portion, right? We should gather this and make a single full portion to, let's say, print it on screen. So this is performed using gather function. Everybody has their local primes. We gather all of this data and then we sort it and print it on screen. So if you want, you can look into the details, but they are quite mathematical and can be a little bit complicated. Just remember these things that I have mentioned to you. I'm not even sure whether I will upload this code, but remember that you don't have to look many details into it. It is important for you to understand these functions, MPI broadcast, MPI gather, and why they are called here, but not much of anything else. This program is run a bit differently than the others that we have run before. Let's try. So MPI exec. Let's try to. Then we call Python. Then C parallel. And please note here that it has one argument. If you remember our first class, sys.rv is actually a list of arguments that is that we have here. If you do not provide the argument, then it will look all the numbers until 100. So if you just press enter, it will find prime numbers. Sorry, MPI exec. I'm missing. You see, then all the primes up to 100 are 2, 3, 5, 7, 11, 17, 19, 23, and so on. Let's not read all of them, but those are the primes. If you don't specify the argument. If you specify the argument from, let's say, 10, then it will find all the numbers up to 10, and this is just 1, 2, 3, 5, 7. Yeah, I mean, for 1, it is not really decided whether it is prime number or not. So in this case, it says that it is, but in most programs that I have been written, we are actually starting from 2. 1 doesn't count. Whatever. It's mathematics. We can try, let's say, 100. And then these are the values. Okay. We could print them a little smarter, because this returns an numpy array, and you have this numpy, you see, np.int, but it really doesn't matter for now. The next thing that I would like to show you is that if you remember yesterday, I told you that our computers that we're using at home, our laptops and so on, are not commonly used for parallel programming. We're commonly using computing clusters. You probably don't have the access to a computing cluster. I'll try to show you just how it can work. And commonly using this Mobax term, you don't need to install this for this subject. I'm just showing you in case you sometimes need it. You can connect to another server, to another computer. You go to session here, then you choose the SSH connection, then you type in the remote host. This will be given to you by your provider of cluster, and your username will be also given. Then you click OK and you can connect. It will show something like this. So this is one of clusters that I have a access to, and it is not by my name, but it doesn't matter, and the password is already remembered. So here what you can do is you can submit your job using a PBS, or that's how it's called, system, and I will show you one of the PBS scripts. So once you write that script, it might be in some folder, I don't know. anywhere here. You go to that folder by using cd, don't remember that. If it's already here, you can stay here, and then you type qsub, that's to submit your job or your parallel program to a queuing system, and then the name of the script. I will not run any script, not to, because this is already a busy cluster. But just so you know, qsub and then the name of script. I will show you how a script can look like. Then what you can see is you can track the status of all the other processes, and these are the processes by using qstat -an. Maybe your cluster that you have access to will have some form of different commands, but it is good to see at least one. What you can see here is the name of the job that someone has ran. Then you have the nodes. Computing cluster consists of several nodes, and each of the nodes can have some number of processors. So it's definitely not a single processor environment. It has many processors, and this is the list of processors that are being used by this task. Okay, that's its name, that's its ID, and this is as you can see here, it is using, I think, 12, right? Maybe more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. It's okay. 12 processes are run here, and they are using node 20 and this many processes within the node 20. Okay, you have how much time this takes. I mean, how much time it is running. If it's not running, you can also type in. So qstat is just a general information. qstat -an, sorry, not -an, gives you more information. And you also have show queue, which is like a shorter list of all the processes, show queue. And here you also have the processes that are being idle, that are not executing at the moment. So these are mostly the ones that are being ran and some other. And here you have like more information about them, whether they are idle, whether they are maybe deferred, rejected, or something like that. All these processes are running. Some of them are running on 12 processors, some of them are running on 4. So actually we are having 12 processes and they are running on 12 processors. We have their start time and something like that. When we want to exit, we type exit and we disconnect. Once we have the results, we can of course download it from the server. Doesn't matter where they are, you just click download and that's it. Okay. So that's just in case you sometimes need that. Then I should show you a PBS. I will give you this manual. This is manual how to write that PBS script. And an example of PBS script, I'll show you. This is a subscript. So if you remember, I typed qsub and then I told you I will not be giving a name of a script because I do not want to run a new job on a cluster. But this could be the name of that script, eratost.sub. So this is the one that is doing the sieve of Eratosthenes. This command is giving the name to your job. So let's say Eratosthenes. Then you will say to which queue you're submitting this job, and then you'll say how many nodes you need. For example, you need 2 nodes. You can be even more specific here and ask for 2 specific nodes. Then if it is needed, you can load an MPI model. And if that is needed in your environment, maybe not. And then you just run the simulation. Here it is instead of MPI exec, that is a Linux system, Linux Scientific, and they are using MPI run instead of MPI exec. Usually you are not specifying here the number of processes. You are specifying number of processes here using this -l nodes and so on. So that's how, if you ever have the chance to work with the computing cluster, you'll probably be writing scripts like this. Maybe it looks kind of weird, but once you write one, then all the others are very similar. So when it works, it's easy. Okay. Let's check maybe some more examples of scatter, of broadcast. I think we went through that fairly quickly. Yeah. So this is just one example. This pprint is from another module, and this module I'll show you. Has only a pprint function that is receiving a string that needs to be outputted on screen, an end that has to be printed, and it has a default communicator, which is MPI control. So all 3 of these can be specified, but all of 3 of these already have values. If you don't specify anything, new line will be printed on screen, and that's it. Okay. But if you specify, for example, this str, then that string will be printed on screen. But only by a zeroth process. Okay. So if you call pprint from this module, only the zeroth process will print str on screen, the str value, not the str as a string. So this will be some text. It will print new line, and then that's it. So here in broadcast, this pprint is actually that print that I have shown you, not just irregular. So the zeroth process will print 78 dashes. Then it will print running on this many cores. It will be the number of processes. This comp size is the number of processes. Then it will print once again 78 dashes. Then comp barrier, it is not necessary in this code, you can delete it, but it is just to synchronize to all processes to come to this line at the same time. When they come to this line, then they continue to the next, and then here we have the n, which is value 5, and everybody has this. All of the processes have this. They are all executing this line, and then if we are zeroth process, then we are executing this line. All the other processes are executing this line. Okay, because of the condition. If we are process 0, if this is true, then we are creating a numbers. Then we are creating a list of n numbers, and we are using the arrange function, which is already familiar with you. Those are the numbers from 0 up to, until 5, not including 5. And here they are. It is decided that they are floating numbers. Maybe this NP won't work. We will try. All the other, this is what the zeroth process has. All the other processes have the empty array, but it has a place for 5 data. It has a storage for 5 data. The data is empty, nothing is there, but the memory is there. And then we are broadcasting from process A to everybody. What? We are broadcasting the A as NPI double. So this float 64 is actually a double precision number. Float 32 is a single precision floating number. I don't know if you have seen this before, but if you haven't, you'll see it now. And let's try this. If it doesn't work, I'll try to fix it in place. So let's do a single process, NPI exit minus NP1 here to broadcast. Oh, sorry, I forgot the word Python. Okay, works. So zero process has everything running on one core. That's okay. Let's try 8. I don't have 8 cores. Well, actually, let's try 16. But the program will print running on 16 cores because we are running the 16 processes. And this is what we get running on 16 cores. And we have everybody has the same data because we distributed them from the zeroth process to everybody else. Okay. Let's try scatter and getter. What we have here so similar is as before, only the zeroth process is printing this on screen. Then we have some value, and if we are a zeroth process, we are creating numbers from 0 up till 4. Also note that this my n is 4, but n is my n times the number of processes. So if we are running 5 processes, this will be 20. If we are running 2, this will be 8. If we are running just 1, it will be 4, and so on. If we are zeroth process, we are creating the numbers from 0 until n. If we are not there, we are creating an empty array. Okay, and then we are creating a larger empty array. So this A is a smaller empty array with only n values, and this my A has this 4 times the number of processes values. If we perform scatter from A to my A, we will change something. And let's check what we obtained here. Let's comment everything else. So comments in Python are written by this, multi-line comments are written by this quote signs. But you should have 3 of them in order to comment on more lines. If you want to comment on a single line, that should be this hash sign. Let's check what we are getting here. So let's do, I don't know, 2 processes. And let's start this third one. So what we have values from 0 until 4 on the zeroth process. And then that's the zeroth process. And then for processes 1 and 2, we have something like this. There will double. Just a second. My A. Okay, so here we are going through all of the processes in this loop. That's to check this part of the code. And then if we are current process, so everybody is looping through all of the processes. You don't have to write it like this, but once you reach yourself in this loop, your own ID, then you print your own data, and then everybody waits. Why like this? Because maybe it is even smarter to perform this barrier before. Let's try it once again. Just check. Yeah, I think it's pretty. Whatever. So this is the number of processes. Once you reach yourself, you print your own ID in a brackets, squared brackets like this, and then you print your A, which has been scattered. Okay. Let's print also this n. Let's debug this. So yeah. Let's print n. And then let's okay. Let's see that first. So this n is of course 12 because we're running 3 processes. We have 4 here. 4 times 3 is 12. So we have 12 printed 3 times because all of 3 processes printed this number. If we wanted just a single process to print it, we could use that function pprint that we saw in a module, or we could say if comrank is equal to 0, sorry, then print it. Of course, now just a single time we see 12 on screen on output. Okay, that's that part. Here we can print the value of A and my A before scatter. I think that's smart thing to do. Let's print it like this. So we'll print A and my A. These total lines. Maybe we should also mention which one is which. We have A and we have my A. So for process 2, those are the values before. So it's practically these values are very small. They are to the minus of they're very close to 0. So that's 0.000 and so on. They're both empty, but once we scatter, they're only full at which processor? They're at which process? Only at the 0, right? Trying to find. Did I print for 0? Yeah. For 0 here. For 0 process, the A is 0, 1, 2, all the way up to 11. So this is like a larger set. A has all the values, not all the way up till 4, all the way up till 12, all the way if we have 3 processes. and smaller a is all the way until my n, okay? So it has 4 values. And what we are doing, we are scattering this large area, which has values that are from everything between 0 and the number of processes times 4 minus 1. So in this case, we have 3 processes. We have my n that is 4. So 4 times 3 is 12, and we have all the numbers between 0 and 11. And then we are dividing this, we are scattering this among the processes. So 0th process would have 0, 1, 2, 3. First process would have 4, 5, 6, and 7. And first process would have 8, 9, 10, and 11. This is what scattering does. So as we can see, after scatter, 0th process has this. First process, that's here, has 4, 5, 6, and 7. And the last process, the second process, has 8, 10, and so on. Let's remove this printing because it's a bit confusing. Let's leave only this after scatter, and let's try with a larger value. Let's try with 12 processors. Actually, let's try to increase this to, let this be 10, right? Let this be 12. So this is what we'll get. We'll have 12 times 10, which is all the values until from 0 to 120, but not including 120. And 0th process would have the first 10. First process will have the next 10. Second process the next 10. So in these brackets are the processes indices, and in these brackets are the values that processes have. Do you have any questions about scatter maybe? I believe it is very hard to focus, especially after how many, more than 2 hours of almost 3 listening to the same person. It is not easy, but okay, it is what it is. Okay. So here we try the scatter. Let's try all gather. How we will perform all gather? We want to collect data into A again. So we have the A, and here we are multiplying it by 2. So we are changing it, my A, we are changing. So this is smaller. These are the chunks that are already divided. And if we multiply all of the chunks by 2, and then perform all gather, then these multiplied chunks will be gathered together into a single large chunk, okay? And we should see like the numbers doubled here. But we performed the doubling only on small chunks, only on this my A, not on this A that is a full array. Let's try now. Okay, we can try it like this. So we have doubled the values. So we will have the values from 0 to and so on, all the way up until 238. Since we have how many processors? We have, sorry. I forgot with how many, with 12, and each has, I think, 10 data. And when we multiply, we will get a number that is 190 times 2, which is 238. So we succeeded in doubling even this all gather. Please note that all gather is the same as gather plus broadcast. If we only performed the gather, we would only have this large A, double A, on a single processor, for example, process 0. But here we have, for all the processes, we have the same this same data doubled in a large array. Okay, let's gather. And let's see what else I have prepared. Just a second. Okay, what we should do now is like try to measure the performances of the different things that we have written. And one part of your seminar work will definitely involve that. You will either write your own code or use help with ChatGPT and so on, or maybe even use some codes that I have written, and then you will perform the analysis. You will increase the data, maybe the data size, and then run the same program with 2 processes, with 5 processes, with 10 processes, and check how the performances go. I will do this. Let's do this with, we kind of did it with Monte Carlo's code. Maybe we could do it again, but a bit more analytically. Second. Yeah, I can close this, I can close this, I can close this. We can use Monte Carlo and NCIP. I think those two are the best. Actually, we could compare first Monte Carlo collective and Monte Carlo point-to-point communication. And that could be fun to do, I think. Let's change something a little bit. Let's measure just this. Let's measure the amount of time that it takes to perform this line 13. So how would we do that? Start on, I'll name it like this, npi dot wall time. So we are getting the time that is needed here. And then we will be getting the time after the reduction function. And then to know how much time has passed, we should do this, right? Time is equal to this. Okay, so before we call the reduce function, time after we call the reduce function, and when we subtract the end and starting time, then we will get how long it lasted. And only the zeroth process should print it. So I will call pprint. Pprint already prints just for the zeroth process. At time of reduce is, and then we will see how much it is. And we should do something similar with point-to-point, but let's check if this works first. So npi exec minus NP. Let's run just one process. Let's run just one process. Oh, let's check what number is here. Let's put first small value just to see if things work. Oh, we have some kind of error. pprint is not defined. Oh, because pprint is in parautils function module. So from parautils import pprint. Let's try now. Because no more says no module. Let me check. Or maybe these are in different location. Okay. Let's use a regular print function not to lose any time here. So print, but only print if rank is 0. Okay, time of reduce is very small. We only had one process. When we have two processes, please note that time of communication rose, right? The execution time also rose because we have small number of points, which is 100, and we have two processes. We used a lot of time on communication, right? So the time that is being used on calculation and communication will be added together, let's say in a total time. Here we have a total time. This is the elapsed time. This is total time. This is time that is used for calculation and for communication. And this here, com time, is just time that is being used for communication. The larger the amount of processes, the more communication between them we need. That's one thing that is important. On the other hand, if we have a large data set, very large data set, it is useful to have more processes to deal with those data. They will do it faster. So we have to balance out this time that is being wasted on communication between processes and this time that is needed for calculation. The communication time should be a small portion of total time, right? That's a good approach. Of course, for 100 points, as I mentioned many times before, it is not necessary to use high performance computing. It is standard computing is totally okay here. Let's increase to 1 million and see what happens then. Let's try a single process. So 1. We see here that reduction time is fairly, the time for communication is fairly small, and the total time elapsed is like this. That seems okay. So now let's try 2 to see if it's worse or if it's better. It is better now, right? We have 1 million points. 500,000 points is calculated by one process, the other half by the other. And you can see here that communication time didn't increase by a large margin. The total time decreased, which is good. So they calculated faster. Let's try 4. we're having some error. That's the error for the seed. Let's change that. Let's put just ID. As I told you before, sometimes it is good to change this. Okay, but I will rerun with 2 and with 1. So this is when we run with 1 process, when we run with 2 processes, and when we run with 4 processes. So far, so good. But what we can note here, this took 1 point something seconds, this took 0.6, this took 0.4. So the best is for this 4. But we can also note that time for communication increased a lot. Let's try 8. For 8, even better. Let's try 16. And now it is starting to decrease. You see, we reached a good performance here, 0.37. The communication time was very fast. It seemed to be good for our problem, but for 16, our communication time increased, and also our execution time increased. Let's try with 32 to see what happens. So yeah, it is starting to increase. 32 processes, and we are having, it's larger than with 6. Let's try with 64. Oh, I ran too many processes for. My laptop will explode. Just kidding. Okay, but we noticed something. All the way up till 8, maybe we should try with 10. 10 is already a lot. Yeah. 10 is 0.41. With 8, we have less, right? Let's try maybe 7, something around 8. 7 is a good number. Let's try 6. Okay, so we reached our minimum with 7 processes, and maybe with 7, 8, that was a good execution time. So it looked something like this. Let this be time of execution. So the larger the value here, the more time we need to finish our program. And let this be the number of processes. We had one time when maybe we can graph this in Excel or something, whatever. One execution time with a single process, then it declined with 2 processes, declined with 4 processes, then let's bear with 2, then with 4, it declined. It even more declined with something around 8, and then after that, time started to rise again. So we have something like this. The communication time usually, not always, because some other things are included, but usually goes something like this. The more number of processes, the more time needed to communicate with them. That's the communication time. And the execution time, generally, with a large number of processors, declines. But when we combine these two, so the calculation time, sorry, this is the calculation time, this is the communication time, when we combine these two, we actually get something like this. Until a certain point, it is good to have to run more processes. Of course, it is problem dependent. But after that point, you shouldn't increase the number of processes because you're wasting your time on creating new processes and you're wasting your time on communication between them for the problem of your size. So for the problem of with 1 million points in Monte Carlo, it would look something like this. Let's try to increase to see what happens if we have 10 million. If we have 10 million, if we have 12 million, this took, if we have 10 million, this took around 12 seconds. Communication time was of course small because only we had one process. If we have two processes, okay, we doubled the time, which is good. This seems okay. This seems right. We doubled the number of processors, and we finished almost twice as fast. That's good. Let's do 4. The communication didn't took quite a while, so that's okay. With 4, okay, almost not double, but it's still good. Let's try 8. And let's try 16. Actually, it also depends on the number of the quality of your processors, or sometimes the environment can be very heterogeneous. You can have different processors. Some of them are faster, some of them are slower. So this will affect the performance too. It is not as simple as the number of processes and the how large the data is and how many communication you have. But we can try to simplify. As we saw before, with 16, it starts to get worse. So it's similar as before. The execution time decreases when we increase the number of processors, but we shouldn't you also use too many. Let's see how much time is wasted when we have point-to-point communication. That's important too. So let's copy this code. Here. In this code here below. So in that other version, these lines were replaced by reduce. Let's have this here. It's okay. Let's make sure that the number of points is the same. And let's run in another terminal. Let's run this the same thing, just not a Monte Carlo collective. Am I sharing the screen? I think I am. Yeah, I got scared for a second. Monte Carlo point. MPI exit 1. Maybe I have copied something in a weird manner. Yeah. Okay, I think we should do it here. I don't know what's happening. MPI exec minus MP1, then Python, then the name of the program. Okay. And let's wait. So what we have here is Monte Carlo collective with 1, 2, 4, 8, and 16 processors. So here, time of reduce actually seems seems good. That's with one. With one processor, we have approximately the same behavior in both of these versions. Let's see what happens when we have two. This communication here seems faster because we have single processor, single process. But what happens when we have two? When we have two, see here that this time there is a lot of time that is being wasted on communication compared to this, where we have two processes, but we use the efficient function. We use the reduce instead of sending and receiving in a linear way. We could re-implement this by using just send and receive, but in a smarter way. Not like this to send to everyone, but like I drew those sketches. It would take some time to implement this. We already have built-in function, so you will kind of let's say have to believe me that this reduce uses those sends and receive, but in a smarter manner. Let's try to increase the number of processors. So we see here that it is important to write. Once again, what it is. That's because of this. Okay. So here, let's compare to the other one. We have 4 processes and something like this. So for 4, it actually went better. But let's try with 8. Okay. With 8, we have something like this. So it is lower, 4.53, and we had 3.37. And with 16, okay, with 16, time of communication is a lot larger, and this is a bit larger than with the other approach. These printing statements could also be kind of misleading, and of course our processes are not running on their own. This process I have on this computer, I have many things that are running at the moment. So of course we should note that this can affect our performance measure too. When you're doing the analysis of this type, it is good to turn off everything else. So I couldn't turn off, of course, Teams and the things I'm showing to you, but it's a good. I think it is a good idea to just close everything else and only run this analysis only one at a time. Maybe you should, it's not maybe, you should do it statistically. You should run a few times your code on a single process, then a few times on 2 processes, then a few times for 4 processes, 8, 16, and so on, and then measure all of the times and get the average. And then you say, okay, this is my average performance with one processor, with one process, with 2 processes, with 4 processes, with 8, and so on. This is my average communication time with all of this. And then you say, okay, this number of processes is optimal for the problem that I have on this and that machine, on this and that processor, and so on. Okay, let's try to measure the performance of Sieve. So let's use start time. We can do it here. Start time. I think does it have already? No. Okay, we should write it. The starting time, the ending time is just before the return. So here. And if we are process 0, it is. If we are process 0, then we should write on screen. Oh, sorry. Then we should write on screen total time is. This elapsed time. Okay, let's try, and let's try it with 100 numbers. So MPI exec minus NP, let it be a single process. Okay, the total time is this. Maybe we don't need to see this, so I will comment this. We are just interested in time, so nothing else. Okay, we know that the program works, so we don't need to see the result here. Okay, with 2 a bit faster. With 4 slower. So okay, here we reached pretty fast with 100 numbers. We reached pretty fast our optimal process number, which in this case, no, in this case it really is the faster using just a single processor. Let's try to increase the problem. Let's try 10,000. Okay. Okay, so a bit faster with 2, but we expect it to be even slower with 4, right? Oh no, it's faster with 4, great. With 8. Okay, and with 10,000 numbers, what we can see here is we are decreasing little by little until 4, and then somewhere around 4 processes, we are starting to have an increase in time. We are losing a lot of time in communication between processes. Let's try to increase this even more. So I'm not sure this is, let's try 1,000,000. Okay, faster with 2, but even faster with 4. A little bit faster with 8. I don't think I will be able to. Okay. My environment doesn't really have more than much cores, so creating this many could not be beneficial. Maybe we could try also on another computer just to check the difference. Oh, I don't think I have installed it in any of these. Okay, we'll stick to this one, not to waste the time. Okay, so this is the total time elapsed. Where do we communicate here? We communicate here using gather, so that's one form of communication. And we communicate here using broadcast. It would be a good idea to measure these two also. So in the same manner, behind gather, we'll just call it and gather time. I will call it G time. Elapsed G time, and the G time is start G time. Start G time we will acquire here. Okay, and then we will print as before. So we are printing elapsed G time. Okay. So this is just for the analysis. It is really not necessary in order to solve this problem. Better analyze it. It is. And we have broadcast here, and I don't think we have anything else. So let's call it elapsed B time. B time, elapsed B time. Broadcast time is, and what we are missing the start. Just a second. Start B time. So before we run the broadcast function, we run this start B time and get the current time. After we run the broadcast function, we call again read time and get the ending time. We calculate the difference between the ending time and the starting time. Oh, this should be. And that's our elapsed time for broadcast function. Similarly, start G time before we call the gather function, and G time when we end the gather function. Elapsed G time we will get when we subtract these two. And let's see how things go. We run it in a single process. Broadcasts seem to be a little bit faster than gather, which makes sense. Okay, with 2, with 4, with 8, sorry, and with 16. Okay, so similarly as before, the total time starts to decrease until it reaches a minimum, and then it increases again. The time that is needed for communication usually increases when we increase the number of processors. I say usually, you see here that sometimes can decrease, but it generally increases for both broadcast and gather. And we also note that gather here is a bit slower than broadcast, which makes sense because it is working with larger data. It has more operations here to do. Okay, are there any questions from your side? This was probably very tiring because it took quite a while. but I think we will finish soon, maybe in 10 or 15 minutes. What we are left with, we should do something that is often done in neural networks. We should write programs to multiply matrices and vectors together, and we should parallelize them. That is maybe important lesson. We will do this not next week, but the week after that. We will take a break. But as regarding to functions and programming itself, we took care of almost everything. Also regarding the decompositions. So we learned cyclic decomposition, we learned the domain decomposition. We had one example where we didn't have to decompose the data at all. That was the Monte Carlo simulation. We learned point-to-point communications. We learned collective communication, broadcast, reduce, scatter, and gather. And that's about it. Do you have any comments? I mean, whether this is like easy or difficult? Do you understand it, or do you think you will need a lot of time alone to read these materials? You don't have to comment if you don't want, but it is it is useful for me as a feedback whether the materials are maybe too hard. Has anyone tried to run one of the codes? I mean, I don't know everyone's background. Actually, I don't know none of your backgrounds, so I don't know how much experience you have. Okay, if it was understandable, then that's okay. I mean, we will see once we give you the assignments. It won't be difficult, but it is expected of you to have everything installed. I mean, you can use different environments too. That's okay. If I am actually using MPI for the first time on a Windows operating system, I usually use it under Ubuntu or Linux Scientific, and I'm mostly using it in C. So this is kind of different for me too. But I think this is much easier actually. In Python, functions are a lot shorter. You can write things in fewer lines than in C for sure. So yeah. In assignment, once again, expected of you is to have everything installed, to have MPI installed under Windows or under Linux. It's okay in both cases, Ubuntu or whatever you're using. And it is necessary for you to run some kind of analysis that I performed. So you should run your programs on one and multiple processes and see what happens. See how much time the process wastes on communication, see how much time they need for calculation. And that compared to say for this problem, for for this data set or for this number of points as we had in Monte Carlo, my performances were like this. Just please do it statistically. I just show you how to run one. You should run it a few times just in case. And to conclude, to say, okay, on my computer, with this and this processor, the most efficient was when I ran it with 4 processes. Sometimes these were, you see that I got them confused, but sometimes they're even used in an MPI literature in the same way. Processor and process. It is, of course, a totally different thing. Process is program that is being ran, and processor is, of course, the hardware thing that is during the computation. Okay, maybe really quick. Let's try one more code. So let me see which one. Let's try to fix this summation. No. So here, what we could fix? We couldn't scatter this data. Why not? Because we used cyclic decomposition. With current knowledge, we couldn't use scatter here. If we used domain decomposition, we could scatter. Let me explain why. So with cyclic decomposition, we are doing something like this. P0 is processing this, P1 is processing the element next to it, P2 the element next to it, and so on. And then again, P0 is processing this element, P1 is processing this element, and so on. And then again, P0, P1, and so on, so on, so on. With domain decomposition, just to repeat, we have all of these elements here processed by the process P0. Then we have all the elements processed by process P1. And if we have full data at process P0, we could use scatter to, let's say, to divide the data among processes and not use this send and receive like here. But since here we use this cyclic decomposition, let's leave this like this. Let's not complicate things too much. What can we change here is all of this can be replaced by a single function, by a reduce function, right? And we'll just copy it from another code. We have it here. So what should we change? This should be local sum. We are performing the summation, okay? And we can call it total sum. You can even print this total sum for everyone can print the total sum just so you can see that only the zeroth process has the valid value. We should comment on these lines because we replaced these lines, this send and receives and this summation by just simply using this reduce plus. This is more computationally efficient in terms of communication and so on. Okay, let's try this code. Maybe I broke it, maybe it doesn't work now. Hopefully not. Okay, you can see here that only the zeroth process has actually the valid result, and all the others have none. That's because we specified this. If we said if we say reduce all, I think it's written like this. Maybe it's written like that. I'm not sure by heart. We'll check. Try like this. Okay, it's not like that. Maybe it's all reduced. We will try many combinations. Okay. Try like this. Okay, it's all reduced. So all reduce is the same as doing reduce and then doing the broadcast function after it. When we are doing reduce, we are specifying who the root is. And then the result will only be at that process, at process 0. All the others will have, as you saw, nothing inside of that variable. But if we want everyone to have the data, we could use all reduce, or the other way to do this is to call the broadcast. So this, maybe we have something else here too, where it's easier to copy. This is reduce. We had broadcast here, right? Maybe not. No, we had broadcasting only here. Okay. Okay. We could broadcast it here, but we are not broadcasting small primes. We are broadcasting total sum from the process number 0. And this is the same as writing reduce all practically. Let's try. Yeah, that's it. That's the effect is completely the same, but this is just a shorter way of saying that if you need. In this case, it's really not necessary for all the processes to have the total sum. So the regular reduce was enough. That is more efficient. I will leave it like this, just so we can compare. All reduce should of course take more time. And let's do both. So start all reduce. And all reduce. And then let's print the elapsed time of all reduce. It's okay. Let's do it like this. Okay, and if we are 0th process, then we will write the time all reduce time, and we will let's print the elapsed time. Okay, let's see. All right. That was an error. Why? Oh, it's again, I forgot the word Python. Okay, all reduce time is okay like this with one process. Let's try it with 2. Let's try it with 4. Let's try it with 8. And maybe stop there. Okay, so it is increasing, if I see correctly. Yeah, maybe it decreased a little bit here, but it is generally increasing. Okay, and what happens if we have simple reduce. Okay, so only one process will have the correct total sum, but that's okay for maybe just him should print just process with rank 0. And let's see if this lowers the communication time. It should. We'll compare 2, 4, and we did with 8. So let's see. Here was with all reduce. I forgot to remove the all from when printing, so reduce time, I should say. But okay, I think you will get it. With 8 processes, all reduce time was 0.0145. With just reduce, so no all, just reduce was less, right? And we can see here that time is usually better than it is almost double the time efficiency when we are using just reduce, because we do not have that broadcast component after. So auto reduce should be used only if you truly need that result to be on all processors, all processes. Maybe when you need that result for to continue your computation, then yeah, then you should use auto reduce. Okay. And let's finally try to measure the full execution time of this program. So let's start the measurement here. Let's call it start. Let's put the end here. And let me not forget this total time. And let's see how things go from here. And we will finish so very soon. The total time for one process very small. We expect this to be worse, right? Because we are having, yeah, it is worse. We are having a very small number of data that we are working with. So when we are raising the number of processors and number of processes in general, we are wasting more time on communication than we are doing the calculation. So what we could try to extend this to make this number larger. Let's try something like this. So this is the summation of all the first, all the numbers before this one. If you remember, there is a smart way to do it. In a single line, the sum is equal to n times n plus 1 divided by 2. But, you know, just in case we want to practice the summation of elements within an array, we can do something like this. Okay, let's try now. And with 8, I'm just trying to find it. Okay. I don't know if you noticed, but when you type the commands in prompt, you can just push the arrow keys up and down and try to find the command that you want. You don't have to type the command from the beginning. Sometimes when you are starting to type your command, then you can press tab, and it will fill the words. So yeah. Let's increase the number even more. Here what we have is that it's still the fastest with only 1. Let's increase more. This is 1 million if I see correctly. And let's try now. With 1 process, with 2 processes, it's still faster with, I'm sure I'm not changing the right value, yeah. It's still faster on a single processor. Okay, now let's increase even further. The word Python is missing. Okay, so the time increased. And now it's still increasing with 2. So we are doing a lot of communication here. We would have maybe something like this. And we will stop here once we perform the, we'll just wait for the program to finish. Maybe I overreacted. How many zeros are here? Okay. That is quite a while. Quite a lot. Yeah, I'm using way too much memory from my laptop. Okay. Okay, so here we have some form of speed up. And then we see with 1 process, it took 1.43, with 2 it took 1.17, which is faster, and then it started to rise. It's still less than with 1 process, but it's starting to rise, so maybe it's not a good idea to run it with 8, but let's try anyways. Okay, yeah, so it definitely is decreasing towards 2, and then maybe 2, 3 processes, maybe even 4 is okay. We will speed up the computation, but anything larger than that will give us a decline in our performances. So for today, I think this should be it. Any questions or comments from your side? If not, maybe try to go through all of this once again, because we will have 1 break. You will probably forget many of the things that I said or I showed. So in the meantime, maybe try just once to skim fastly through all of this, so we can continue in the week after. Okay. See you next time. Bye.
Thank you. Goodbye.
Thank you for the lecture. Goodbye.